Now, in this lecture, we'll find out the area of the green shape. In the drawing, we have a circle. Inside this quarter circle, we know that the radius of this small circle is equals to the square root of 2 units. And our mission is to find out the area of this green, the area of the green shape. So first of all, we define the relevant points to this question with letters. We define this point as A. We define this point as B. We define this point is the center of the quarter circle, therefore we define this point as O. We define this point as C. We define this point as D. This point is the touching point between this small circle and the quarter circle. We define the touching point as E. And finally, we define the center of this small circle, this point, as F. In the next step, we join points F and C together by straight line. What is the definition of line segment FC? Point F is the center of the small circle, point C is the point on the small circle itself, therefore FC is the radius of this small circle. The radius of this small circle equals to the square root of 2 units according to what is given us in the question, therefore FC equals to the square root of 2 units in its length. We can implement in our drawing here rule 1. I'll remind you quickly what is rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. In the drawing we have a circle and we also have this tangent AB that is tangent to this circle at this point, point M. Point M is the point of tendency of tangent AB with this circle. And we also have the radius OM is equals to capital R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, rule 1. Can I implement rule 1 in our drawing? Why? Because in our drawing we have the radius FC that is drawn to point C. It's actually the point of tendency of tangent OD with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. If OD is perpendicular to CF, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we have here the radius FB of this small circle that is drawn to point B, that is the point of tendency of tangent AO with this small circle. And whenever you have a radius that is drawn to the bottom, to the point of tendency, then tangent AO will be perpendicular to the radius BF. If AO is perpendicular to BF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, we will focus on this small quadrilateral FBOC. Inside this small quadrilateral FBOC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of this fourth angle. In total, they must be equal to 360 degrees according to the rule. Then the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing fourth angle here must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles in this small quadrilateral BFOC to 360 degrees, the fourth angle must be equal to 90 degrees in its size. So actually found out that inside quadrilateral BFOC we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to this small quadrilateral BFOC as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle BFOC, side BF must be equal to the opposite side OC. But BF equals to the square root of 2 units, therefore OC must be also equal to the square root of 2 units in its length. Likewise, according to the same rule, side BO must be equal to the opposite side FC in rectangle BFOC. But FC equals to the square root of 2 units, therefore BO must be also equal to the square root of 2 units in its length. So I actually found out that this small quadrilateral BFOC is not a rectangle but a square. Why? Because all of its sides are equal to each other. Each side of this quadrilateral is equal to square root of 2. Okay, in the next step we'll join points O and F together by a straight line. By joining points O and F, we get that the right triangle OBF. In the right triangle OBF, side OB equals to side BF. They are both equal to the square root of 2 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So those 2 angles that are located in front of those 2 equal sides must be also equal to each other. So if we define this angle as alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in this right triangle OBF must be equal to 180 degrees. So which angles we have inside the right triangle OBF? We have this angle that is equal to 90 degrees. This angle equals to alpha, and this angle also equals to alpha. So 90 degrees plus 2 alpha, in total they must be equal to 180 degrees according to the rule that I mentioned in the right triangle OBF. Here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees, so 2 alpha equals to 90 degrees. Here we divide this equation by 2 and finally we get that the missing angle alpha equals to 90 degrees over 2 is 45 degrees. So this angle alpha is equals to 45 degrees in its size. and this is also angle alpha that is equals to 45 degrees. We will continue to focus on the same right triangle, triangle OBF, this right triangle, triangle OBF. Here we'll implement the Pythagoras theorem on this right and isosceles triangle, triangle OBF. In the right triangle, triangle OBF, here by PT is the evaluation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, the hypotenuse in this right triangle, the hypotenuse in this right triangle OBF is OF, therefore the square of the hypotenuse is OF squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to FB squared plus BO squared. Repeat again, in the right triangle OBF, according to the Pythagoras theorem, OF squared equals to FB squared plus OB squared. So OF squared, that is the square of the hypotenuse, is equal to FB squared. FB is square root of 2, therefore FB squared is square root of 2 squared, that is 2, plus BO squared. BO is also square root of 2, therefore BO squared is square root of 2 squared, that is 2. So in conclusion, we found out that OF squared equals to 2 plus 2, that is 4. OF squared equals to 4. Here we take a root out of this equation, and we get that OF equals to the square root of 4, that is 2. So the length of the hypotenuse OF is equals to 2 units. Here OF equals to 2 units in its length, so I write it down here. In the next step, I will present to you a new rule, and we'll implement the new rule in our drawing. The new rule is rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together must pass for their touching point. So in the drawing we have two circles. This small circle is located inside this big circle. Therefore, we have here an internal notch between those two circles. That is to say they are touching each other internally at point P. So whenever you have an internal notch between two circles, like in this drawing, that the straight line that connects the centers together, here point O is the center of this big circle, point M is the center of this small circle, and the straight line that connects their centers together is the straight line OM. And according to this rule 9, the straight line OM must pass for point P, that is their touching point. Or OMP is one straight line. OMP is one straight line. You can also say that all the 3 points O, M, and P are located on one straight line. We can actually implement this rule 9 in our drawing. Why? Because in our drawing in our drawing, first of all, we have an internal notch between this small circle and the big quarter circle. Why? Because the small circle is located inside the big quarter circle. This small circle is located inside the big quarter circle, and they are touching each other internally at this point E. Point E is their touching point. Therefore, we can implement here rule 9. Whenever you have an internal notch between two circles, you can implement rule 9. According to rule 9, the straight line that connects their centers together, the center of the quarter circle, you can say also the center of the big circle, that the quarter circle is part of it, is here at point O. The center of this small circle is here at point F, and the straight line that connects their centers together is the straight line OF. This straight line OF must pass through point E. That is the attachment point, according to rule 9. Or OFE is one straight line. Again, OFE is one straight line. Okay. So OFE, line segment OFE is one straight line. I write it down. So we know that OFE is a straight line, one straight line. What is the other definition of the straight line OFE? The straight line OFE starts from point O, that is the center of the big circle, and ends at point E, that is the point of the big circle itself. This is exactly the definition of a radius. So OFE is the radius of the big circle. We will define the radius of the big circle as capital R. Therefore, capital R is equals to OFE. Okay, I write it here that capital R is the radius of the big circle. What is the length of the radius of the big circle, capital R? The length is OFE. And we know that OFE is one straight line, and therefore the length of OFE must be equal to OF plus FE. Again, the length of the radius OFE, it must be equal to OF plus FE. OF equals to OF plus FE, and it is also the radius of the big circle. What is the definition of line segment FE? Point F is the center of the small circle, point E is the point on the small circle itself. Therefore, FE is the radius of the small circle, that is equals to the square root of 2 units according to what is given as the question. So the radius of the big circle, capital R, equals to OF plus FE. OF is 2, and FE is square root of 2. FE is square root of 2. So, in conclusion, found out that capital R, that is the radius of the big circle, equals to 2 plus square root of 2 units in its length. So OFE is one straight line. It is also the radius of the big circle. So OFE is one straight line. Here we define the intersection point between the radius OFE and this small circle SH. We know that OFE is one straight line. If OFE is one straight line, then HFE that is part of OFE must be also a straight line. Okay? Part of a straight line must be also a straight line. HFE that is part of the straight line OFE must be also a straight line. So we know that HFE is one straight line, but HFE is a straight line that touches the small circle at points H and E. Any straight line that touches the circle at 2 points must be a chord. So we know that HFE is a chord in the small circle, but HFE is a special chord in a small circle that passes through point F, that is the center of this small circle. We know that any chord that passes through the center of a circle must be the diameter of the circle. So HFE is the diameter of the small circle. Write it down. Line segment HFE is the diameter of the small circle. So HFE is the diameter of the small circle. We know that any diameter of any circle bisects the circle into two halves, or it divides the circle into two equal areas. Any diameter divides the circle into two areas, into two equal areas. So this is the first area and this is the second area, and those two areas are equal to each other. So this area will be defined as a semicircle. Okay. This area is defined as a semicircle, and this area also is defined as a semicircle. Okay. So in the next step, I will present to you the definition of a sector. We have this circle. Inside this circle we have the green shape AOB. The green shape AOB is defined as a sector. So if we look at this circle as a cake, then the sector is one slice of this cake. Okay, again, a sector is one slice of this cake. And the sector AOB, the green sector AOB, consists of two legs. One leg is the AO and the other leg is BO. Okay? Those two legs of this sector AOB, they are both the radii of this circle that is equal to R. And the angle between the legs of this green sector AOB is this angle theta. Okay. The vertex here is the center of the circle. Okay. So what is the area of this green sector AOB? the area of this green sector A or B is equals to the area of the circle is equals to pi r squared times theta, that is the angle between the legs of this sector, over 360 degrees. Okay? Repeat again. The area of the green sector A or B equals to pi r squared, that is the area of the circle, times theta over 360 degrees. Okay? Our mission here is to find out the area of this green shape. So, what is the area of this green shape? The area of the green shape will be equal to the area of the big sector AOE, this big sector AOE. The big sector AOE is part of the big circle. Okay, this big sector AOE is part of the big circle. Here, this line above AOE is the sign for a sector. It means sector AOE, and the square brackets is the sign for the area. So this expression means the area of sector AOE. So the area of the green shape in total equals to the area of the big sector AOE, that is part of the big circle, minus the area of this small semicircle. The small semicircle is of course part of the small circle. Minus the area of shape HBO, this shape HBO. Minus the area of the orange shape, HBO. I'll repeat again. From the drawing it is very easy to see that the area of this green shape equals to the area of the big sector AOE minus the area of this small semicircle minus the area of this green shape BHO. Yeah. The area of the green shape equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape HBO. So we find out the area of each shape and we subtract from the area of the big sector AOE the area of the small semicircle minus the area of the orange shape HBO, and this will be the area of the green shape. Okay, this will be the area of the green shape. So first of all, we find out the area of the big sector AOE. What is the area of the big sector AOE? Repeat again. That the big sector AOE is part of the big circle, and therefore the two legs of the big sector AOE, each leg will be with a leg of the radius of the big circle that is actually capital R. Again, because of the fact that the big sector is part of the big circle, then the area of the big circle is pi times capital R squared times the angle between the legs of sector AOE. This is the angle between the legs of sector AOE. The first leg is AO and the second leg is EO. They are both the radii of the big circle that is capital R. So this angle equals to 45 degrees. You can see here that this angle it is equals to 45 degrees in its side. So the angle between the legs of the big sector AOE is equal to 45 degrees. So the area of the big circle times the angle between the legs of sector AOE, that is 45 degrees, over 360 degrees, that is actually the area of the big sector AOE. So the area of the big sector AOE equals to pi times R squared. And we have already found out that capital R, it is, again, the area of the big sector AOE is pi times capital R squared. And we have already found out that capital R equals to 2 plus square root of 2. If capital R equals to 2 plus square root of 2, it means that capital R squared equals to 2 plus square root of 2 squared. So R squared is 2 plus square root of 2 squared times 45 degrees over 360 degrees. It is 1 over 8 or 1/8. So we have to divide the area of the big circle by 8. So the area of the big sector AOE equals to pi times 2 plus square root of 2 squared. 2 plus square root of 2 squared will be equal to, according to the algebraic identity, that a plus b squared equals to a squared plus b squared plus 2 times ab. We get that 2 plus square root of 2 squared will be equal to 2 squared, that is 4, plus square root of 2 squared, that is 2, plus 2 times 2 times square root of 2 divided by 8. So it is equals to pi. Inside the brackets we have 4 plus 2, that is 6. 4 plus 2 is 6. And plus 2 times 2, that is 4. So in total, this expression will be equal to 4 times square root of 2 divided by 8. So here we will divide both the numerator and the denominator of this expression by 2, and we get that the area will be equal to pi. Inside the brackets we have 6. 6 over 2 is 3, plus 4 times square root of 2. 4 times square root of 2 over 2 is 2 times square root of 2. Divided by, we have to divide the denominator also, the denominator 8 by 2. 8 over 2 is 4. Because we divided both the numerator and the denominator of this expression by 2. So in conclusion, we found out that the area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units. So I write it down. The area of the big sector AOE is equals to pi times 3 plus 2 times square root of 2 over 4 square units. here, the area sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units. In the next step, we find out the area of this small semicircle. This small semicircle is half of the small circle. Therefore, the area of the small semicircle will be equal to pi r squared, that is the area of the small circle, over 2. So it is pi, and it has given us the question that the radius of the small circle r is equals to the square root of 2. If r is equals to the square root of 2, it means that r squared equals to the square root of 2 squared, that is 2, divided by 2. 2 over 2 is 1, so we left only with pi. In conclusion, found out that the area of the semicircle, the area of the small semicircle, is equals to pi square units. And finally, we have to find out also the area of the orange shape, the area of this orange shape. That is actually HBO, the area of the orange shape HBO. What is the area of the orange shape HBO? From the drawing, it is very easy to see that the area of this orange shape HBO is equals to the area of the right triangle FBO minus the area of this small sector, the small sector FBH, that is part of the small circle. So minus the small sector FBH, this small sector FBH. So what is the area of the right triangle, triangle FBO? The area of this right triangle, triangle FBO. We know that the area of any triangle equals to the base of the triangle times the height to the base over 2. In this height in the isosceles triangle, triangle FBO, side FB is equal to side BO. So the height equals to the base. They are both equal to the square root of 2 units. So the base is square root of 2. The height is also square root of 2 divided by 2. Square root of 2 times square root of 2 is 2, and 2 over 2 is 1. In conclusion, found out that the area of the right triangle FBO is equals to 1 square units. In the next step, we find out the area of the small sector FBH. What is the area of the small sector FBH? According to the formula that I presented to you, here, what is the area of this small sector FBH? The small sector is part of this small circle. So the area of the small sector FBH will be equal to the area of the small circle, that is pi r squared, times the angle between the legs of this sector, the angle between the legs, the two legs, FH and FP, the angle between these two legs, FH and FP, this angle is equal to 45 degrees over 360 degrees. It is given as the question that r equals to square root of 2, therefore r squared is square root of 2 squared, that is 2. So in total, the area of the small circle equals to 2 pi square units times 45 degrees over 360 degrees. 45 degrees over 360 degrees, it is 1 over 8, so we have to divide the area of 2 pi by 8. Here we divide both the numerator and the denominator of this expression by 2. 2 pi over 2 is pi, and 8 over 2 is 4. So in conclusion, we found out that the area of the small sector FBH is equals to pi over 4 square units. Therefore, in total, the area of the orange shape HBO is equals to the area of the right triangle FBO, that is 1, minus the area of the small sector FBH, that is pi over 4. So in total, the area of the orange shape HBO is equals to 1 minus pi over 4 square units. Our mission is to find out the area of this grain shape. I repeat again that the area of the grain shape is equals to the area of the big sector AOE that we have already found out, minus the area of this small semicircle that we have already found out, minus the area of this orange shape HVO that we just right now found out. Repeat again. The area of this green shape equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape HVO. So the area of the green shape equals to the area of sector AOE. We have already found out that the area of sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units. Here the area of the big sector AOE equals to this expression minus the area of the small semicircle. We have already found out that the area of the small semicircle equals to pi square units minus the area of the orange shape HBO, and we have already found out that the area of the orange shape HBO is equals to 1 minus pi over 4 square units. So the value of this expression in total is equal to the area of the green shape. So we'll simplify this expression in order to obtain the area of the green shape in terms of numbers. So we have here pi times 3 plus 2 times square root of 2 over 4 minus pi. We will open the brackets here. We have minus before this bracket, so it will be here minus 1. And we have here minus times minus is plus, so it is minus 1 plus pi over 4. We'll open the brackets here, and we get that pi times 3 is 3 pi, plus 2 times square root of 2 times pi is 2 times square root of 2 times pi, and we have divided by 4. And we have here minus pi plus pi over 4 is minus 3/4 pi. And we have here minus 1, so we'll multiply minus 1 by 4, and then we divide it by 4 in order to overcome factor with the other two expressions. Minus 1 times 4 is minus 4 divided by 4. So we have here 3 pi minus 3 pi is 0, so 3 pi will get cancelled, and we're left only with 2 times square root of 2 times pi minus 4 over 4. Here we divide both the numerator and the denominator of this expression by 2, and we get that 2 times square root of 2 pi is square root of 2 times pi, minus 4 over 2 is minus 2, and we have to divide the denominator 4 by 2 also, so 4 over 2 is 2. So if we're going to find out that the area of the green shape equals to either square root of 2 pi minus 2 over 2 square units, or in terms of numbers, it is equals to 1.2214 square units. Repeat again. The area of this green shape equals to either square root of 2 times pi minus 2 over 2 square units, so in terms of numbers, the area of this green shape equals to 1.2214 square units. So in the next step, I will summarize the lecture. In this lecture, we found out the area of this green shape. In the drawing, we have this small circle inside the big quarter circle. In addition, we know that the radius of this small circle r equals to the square root of 2 units. Again, our mission is to find out the area of this green shape. So first of all, we defined the names to the relevant, we defined the relevant points to this question with letters. We defined this point as A, we defined this point as B, this point is the center of this quarter circle, so we defined this point as O, we define this point as C, we define this point as D. This point is the touching point between this small circle and the big quarter circle. We define the touching point, this touching point as E, and finally we define the center of this small circle, this point, as F. Then we join points F and C together by a straight line. Point F is the center of the small circle, point C is the point of the circle itself, therefore FC is the radius of this circle, that is equals to the square root of 2 minutes according to what is given as the question. Here we implemented rule 1, we have the radius FC that is drawn to point C, that is the point of tendency of tangent OD in this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. If OD is perpendicular to CF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, the radius FB of this small circle is drawn to point B, that is the point of tendency of tangent AO with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius BF. If AO is perpendicular to BF, it means that this angle equals to 90 degrees, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside the small quadrilateral BFOC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. Plus the size of this fourth angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore the missing angle here must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles inside this quadrilateral BFOC to 360 degrees, the missing angle here must be equal to 90 degrees in its size. So inside the small quadrilateral BFOC we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral BFOC as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle BFOC, side BF must be equal to the opposite side OC. But BF equals to the square root of 2, therefore OC must be also equal to the square root of 2 units in its length. Likewise, according to the same rule, in rectangle BFOC, side FC must be equal to the opposite side BO, but FC equals to the square root of 2 units, therefore BO must be also equal to the square root of 2 units in its length. So, in conclusion, we found out that quadrilateral BFOC is not a rectangle but a square. Why? Because all of its sides are equal to each other. Inside of this square is equal to the square root of 2 units in its length. In the next step, we join points F and O together by a straight line. By joining points F and O, we created the right triangle FBO. In the right triangle FBO, side FB equals to the opposite side BO. They are both equal to the square root of 2 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle, there are equal angles. So those 2 angles that are located in front of those 2 equal sides must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have inside the right triangle BFO? You have this angle that is alpha, this angle that is also alpha, and this angle equals to 90 degrees. So 2 alpha plus 90 degrees, in total they must be equal to 180 degrees according to the rule that I mentioned. Here we subtracted 90 degrees from this equation, and finally found out that 2 alpha equals to 180 degrees minus 90 degrees. This is 90 degrees. 2 alpha equals to 90 degrees. We divided this equation by 2 and finally found out that the missing angle alpha equals to 45 degrees in its size. This is angle alpha that equals to 45 degrees, and this is also angle alpha that is equal to 45 degrees in its size. Okay. Then we implemented the Pythagoras theorem on the small right triangle, triangle FBO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right triangle FBO, the hypotenuse is FO, so FO square equals to FB square plus BO square. Okay, again, in the right triangle BFO, FO square equals to FB square plus BO square. So FO square or OF square, that is the square of the hypotenuse, equals to fb square. fb is square root of 2, therefore fb square is square root of 2 squared, that is 2, plus bo square. bo is also square root of 2, so bo square is square root of 2 squared, that is 2. So in conclusion, we found out that OF squared, that is the square of the hypotenuse, equals to 2 plus 2, that is 4. We took out of this equation and finally found out that OF, the length of the hypotenuse OF, is equals to the square root of 4, that is 2. Here, the hypotenuse OF is equals to 2 units in its length. Then I presented to you rule 9, as we implemented rule 9 in our drawing. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together must pass for their touching point. In the drawing, we have two circles. Because of the fact that the small circle is located inside the big circle and they touch each other at point P, we have here an internal match between those two circles. That is to say, they are touching each other internally at point P. And according to this rule 9, we have the straight line that connects their centers together must pass for their touching point. The center of the big circle is here at point O. The center of this small circle is here at point M. And the straight line that connects their centers together is the straight line OM. And according to this rule 9, the straight line OM must pass for point P, that is their touching point. So OMP is one straight line. Okay, OMP is one straight line. Actually, we can implement rule 9 in our drawing. Why? Because in our drawing, we also have an internal notch between those two circles. That is to say, first of all, this small circle is located inside this big quarter circle, and they touch each other here at point E. Therefore, we have here an internal notch between those two circles, and for that reason, we can implement here rule 9. According to rule 9, the straight line that connects the centers of those two circles must pass from point E, that is their touching point. The center of the big quarter circle and also the center of the circle that the quarter circle is part of it is here at point O. The center of this small circle is here at point F, and the straight line that connects their centers together is the straight line OF. And according to rule 9, the straight line OF must pass for point E, that is their touching point. Again, the straight line OF must pass for point E, or OFE is one straight line. Again, according to rule 9, OFE is one straight line. We know that OFE is a straight line. What is the other definition of the straight line OFE? We know that the straight line OFE starts from point O, that is the center of the big circle, and ends at point E, that is a point on the big circle itself. This is exactly the definition of a radius. Therefore, OFE is the radius of the big circle. We define the radius of the big circle as R. Here, R is the radius of the big circle. So, the radius of the big circle R equals to OFE. So, what is the length of the radius, capital R? That is equals to OFE. Because of the fact that OFE is one straight line, OFE in total will be equal to OF plus FE. Again, OFE equals to OF plus FE. OF is 2. And what is FE? FE, nice segment FE starts from point F, that is the center of the small circle, and ends at point E, that is a point on the small circle itself. This is exactly the definition of a radius. Therefore, FE is the radius of this small circle, that is equal to the square root of 2 units. So, again, OFE equals to OF, that is 2, plus FE, that is square root of 2. So, in total, OFE equals to 2 plus square root of 2, that is actually the radius capital R also equals to 2 plus square root of 2, because capital R equals to OFE. So, in conclusion, found out that the radius of the big circle capital R equals to 2 plus square root of 2. Then we know that OFE is one straight line. If OFE is one straight line, it means that here edge FE is also one straight line because edge FE is part of OFE. So edge FE is one straight line. It is one straight line that touches the small circle here at point E and here at point H. So any straight line that touches the circle at 2 points must be a chord. So edge E is a chord of the small circle, but it is a special chord that passes point F. That is the center of the small circle, and any chord that passes through the center of the circle must be the diameter of the circle. Therefore, edge FE is the diameter of the circle. So here edge FE is the diameter of the small circle. We know that any diameter of any circle bisects the circle into two equal areas. Each area is a semicircle. So this area is a semicircle, and this other area is also the other half of this circle. It is also a semicircle. So in conclusion, found out that this area HBE is a semicircle of the small circle. Okay. Then I presented to you the notion of a sector. Here we have a circle and the green shape AOB is a sector. So a sector is part of a circle. If we look at this circle as a cake, then the sector AOB will be one slice of this cake. Okay? The green sector AOB consists of two legs. The first leg is AO and the second leg is BO. Both legs of this sector AOB are the radii of this circle that is equal to R. And the angle between the legs AO and BO is angle theta. So what is the area of this green sector AOB? The area of the green sector AOB equals to pi r squared, that is the area of the circle, times theta, that is the angle between the legs of the sector, over 360 degrees. Okay, so the area of a sector is the area of the circle that contains the sector times the angle between the legs of the sector over 360 degrees. Okay. So our mission is to find out the area of this green shape. What is the area of the green shape? From the drawing it is very easy to see that the area of the green shape in total it is equal to the area of the big sector. The big sector AOE is part of the big circle, minus the area of this small semicircle. The small semicircle is part of the small circle, is half of the semicircle, of the small semicircle, minus the area of this orange shape, HBO. And again, the area of the green shape equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape HBO. So what is the area of sector AOB? Sector AOB is part of the big circle. So the area of any sector is the area of the circle that contains the sector. The big circle contains the big sector, and the area of the big circle equals to pi times capital R squared pi times capital R square times the angle between the legs of this sector. The two legs of the big sector AOE are AO and EO. And the angle between the two legs is this angle. That is equal to 45 degrees in its size. So it is 45 degrees over 360 degrees. So in total, the area of this big sector AOE equals to pi times capital R square times 45 degrees over 360 degrees. Okay. Pi times capital R square times 45 degrees over 360 degrees. We have already found out that capital R equals to 2 plus square root of 2. Therefore, capital R square equals to 2 plus square root of 2 square. So in total, the area of the big sector AOE equals to pi times capital R square, that is 2 plus square root of 2 square, over 45 degrees over 360 degrees, it is 1 over 8. So we have to divide the area by 8. So the area of the big sector AOE in total will be equal to pi, and we have 2 plus square root of 2 square, it is equals to 2 square, that is 4, plus square root of 2 square, that is 2, plus 2 times 2 times square root of 2. And we have to divide it by 8. Here we have pi, inside the brackets we have 4 plus 2, that is 6. And here we have plus 2 plus 2 is 4, so in total this expression equals to 4 times square root of 2 divided by 8. Here we divided both the numerator and the denominator of this expression by 2. And we got here in the numerator we have pi, and inside the brackets we have 6. 6 over 2 is 3. And we have also plus 4 times square root of 2 over 2 is 2 times square root of 2. And we have to divide the denominator 8 also by 2. 8 over 2 is 4. So in conclusion, we found out that the area of the green shape AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units. It again, the area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units. In the next step, we found out the area of this small semicircle. The small semicircle is half of the small circle, and therefore the area of the small semicircle will be equal to the area of the small circle, that is pi r square over 2. It is given as the question that the radius of the small circle is r, that is equals to the square root of 2. If r equals to the square root of 2, it means that r square equals to the square root of 2 square, that is 2. So in total, pi r square equals to 2 pi, that is the area of the small circle, divided by 2. If you divide the area of the small circle by 2, we will get the area of the small semicircle. So 2 pi over 2 is pi. So in conclusion, we found out that the area of the small semicircle is equals to pi square units. And finally, we found out the area of this orange shape. What is the area of this orange shape? HBO. From the drawing, it is very easy to see that the area of this orange shape HBO equals to the area of the right triangle FBO minus the area of this small sector FBH. Repeat again, the area of the orange shape HBO equals to the area of the right triangle FBO minus the area of the small sector FBH. The small sector FBH is part of the small circle. So the area of the orange shape HBO equals to the area of the right triangle FBO. What is the area of the right triangle FBO? The area of any triangle equals to the base of the triangle times the height to the base over 2. In this right triangle FBO, the height equals to the base, because side FB equals to side BO. They are both equals to the square root of 2 units. So the base is square root of 2 and the height is also square root of 2 divided by 2. Square root of 2 times square root of 2 is 2, and 2 over 2 is 1. So in conclusion, we found out that the area of this right triangle FBO, it is equals to 1 square unit. And then we have to find out also the area of the small sector FBH. The small sector FBH is part of the small circle, So the area of the small sector FBH will be equal to pi r squared, that is the area of the circle, times the angle between the legs of this sector. The angle between the legs of this sector FBH is 45 degrees. So it is 45 degrees over 360 degrees. Pi r squared, r is square root of 2, therefore r squared is square root of 2 squared, that is 2. So r squared is 2, so in total the area of the small circle is 2 pi, and 45 degrees over 360 degrees, it is 1 over 8. So we have to divide the area 2 pi by 8. Here we divided both the numerator and the denominator of this expression by 2, and found out that 2 pi over 2 is pi, and 8 over 2 is 4. So in conclusion, we found out that the area of this small sector FBH, it is equal to pi over 4 square units. Therefore, in total, the area of this green shape equals to the area of the right triangle FBO, that is 1, minus the area of the small sector FBH, that is 1, that is pi over 4. So in total, the area of the orange shape FBO equals to 1 minus pi over 4 square units. Repeat again that our mission is to find out the area of this green shape. So again, the area of this green shape equals to the area of the big sector AOE minus the area of this small semicircle minus the area of this orange shape HBO. Repeat again, the area of the green shape equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape HBO. We have already found out that the area of the big sector AOE, it is equal to pi times 3 plus 2 times square root of 2 over 4 minus the area of the small semicircle, that is equal to pi square units, minus the area of the orange sector HBO, that is equal to 1 minus pi over 4 square units. So this expression, the value of this expression in total, it is equals to the area of the green shape. So we simplified this expression in order to find the area of the green shape in terms of numbers. So we have here pi times 3 plus 2 times square root of 2 over 4 minus pi. We open the brackets here, we have minus before the bracket, so this expression will be minus 1, and minus times minus is plus. So it is minus 1 plus pi over 4 minus times minus is plus. So here we open the brackets, and we got that pi times 3 is 3 pi, and plus 2 times square root of 2 times pi, and we have divided by 4. And minus pi plus pi over 4 is minus 3/4 pi, and we have minus 1. We multiplied minus 1 by 4, and then we divided by 4 in order to overcome factor with the other two expressions. So we have here minus 4 divided by 4. So here we have 3 pi minus 3 pi, that is 0, so we left only with 2 times square root of 2 times pi minus 4. 2 times square root of 2 minus 4 over 4. Here we divided both the numerator and the denominator of this expression by 2. In the numerator we have 2 times square root of 2 pi over 2 is square root of 2 pi, and minus 4 over 2 is 2, and we have to divide also the denominator 4 by 2. 4 over 2 is 2. So in conclusion, we found out that the area of this green shape equals to either square root of 2 pi minus 2 over 2 square units, or in terms of numbers, the area of this green shape equals to 1.2214 square units. Okay, thank you very much.